Welcome to the second session of our tutorial on federated learning, privacy-preserving machine learning, and how these concepts can be built and explored using the Flower framework. This is session 2. We had a prior session 1 week ago where we covered just the very basics of federated learning and the Flower framework and some of its facilities. In this session, we're going to dive into some really important extensions from this basic set of principles that in particular look at how you can do various kinds of privacy protection and even incorporate some of these latest forms of models in machine learning, such as LLMs. The agenda for this second session will be as follows. We're going to begin with a brief welcome to you all. Then we're going to have a series of lectures by the experts that have joined us today. We're going to start off with a session on a library that we call FlowerTune, but in particular, it'll be talking about how you can do things like fine-tuning LLMs using federated learning. We'll be having subsequently a session on differential privacy and security more generally. We'll also have after that a session just dedicated on secure aggregation. And if time permits, we do have some material that explores some of the challenges that exist within federated learning that we'll get to as well. We'll endeavor to have questions at the end of each of these sessions, but if not, or in addition to, we will have a time at the end for answering your questions as we did last time. I'd just like to say again, a big thanks to Amity University, Noida, and the CSSP Club, who we have co-organized this tutorial and workshop with. They've been great to work with, and we've met through them some fabulously talented students already. It's really been a pleasure giving this series. And I just want to give a big acknowledgement to the organizing team, and in particular from Amity University and by extension, the CSSP Club. We're joined here by Professor Dr. Ashwin Kumar Dubey. And I think he might want to say a few words to welcome us too.
Yeah, thank you, Professor Lin. So a very good afternoon and a very good morning to one and all present here. On behalf of the Communication System and Signal Processing Club of Department of Electronics and Communication Engineering, Amity School of Engineering and Technology, Amity University, Uttar Pradesh. And my own behalf, I would like to welcome all the guests, Professor Lane, Dr. Ian Gao, Dr. Mohammad Naseri, and all the participants who have joined, who come across and joined this wonderful event to learn more related with the federated learning. So from my core of heart, I would like to welcome, and I really appreciate the pain taken by Professor Nick and the entire team for organizing this wonderful workshop. And my big thanks to all my organizing team who have come across and put their effort to make this event successful. So let's welcome and share, let's have some kinds of learning from the talented team of the University of Cambridge, the Flower Lab, and hope so we will be get benefited from their nice talk. So thank you, Professor Nick, for giving me the time to welcome all the panelists. So it's over to you.
Thank you. Thank you. It's a pleasure to work with you and your team. It's great stuff. Let me introduce you to the speakers for today. And so last week you heard from myself and Javier. We talked about some of the basics and fundamentals related to federated learning. Today in this session, we're going to be joined with three research scientists from Flower Labs who are specialists in various aspects of federated learning. And if just going in order that you see them on the screen here, we have Mohammed Nazari. He is a research scientist at Flower Labs. He specializes in security and privacy related topics. You'll be hearing from him in the second speaking slot. We are joined also by Pan Hang. He's a research scientist. He's going to be telling you a lot about secure aggregation. Here he is, just waving at us. And then we also are joined by Yan Gao, research scientist at Flower Labs, who specialized in the past in things like self-supervised learning and how this can interact with federated learning. But today he'll be talking to you about LLMs and how this reacts with and interfaces with federated learning. So welcome to them. The tutorial organization is, as I mentioned last session, everyone who's attending both sessions will get a certificate from us for their attendance and participation and the learning that accrues from that experience. We would encourage you to ask questions, so don't be afraid to ask. Feel free to put your questions in the Slack, and if we can't quite get to them during this live session, we will endeavor to answer them after the session. We're running this as a Zoom webinar, and so there'll be periods when we ask for questions, and at that point, feel free to raise your hand and I can unmute you. You'll be able to ask your question live in front of us all and get your have that discussion. But we also have a facility here for asking questions inside the webinar. So you can ask your questions and we'll take them one by one as they come up during these question sessions. So basically the point here is just feel free to ask what's on your mind, and we'll respond as it sort of flows during the tutorial. Okay, so with that, it's a time to get underway and start to learn something. The first talk we have is by Yan Gao. He's going to talk to us about FL and LLMs and fine-tuning and topics in that direction. So over to Yan. We're excited to hear what you have to teach us today.
Okay, thanks, Nick, and thank you very much for the invitation. So let me share my screen.
Oh, I think I need to enable something. I forgot one thing.
Okay.
There we go.
Cool. I think you can see my screen now, right?
Yes, looks good.
Okay, great. Yeah, so yeah, in this session, I'm going to talk about federated LLM fine-tuning with FlowerTune. So as we all know, the large language model LLM has got remarkable performance in like a wide range of machine learning tasks across different domains, such as the general LP task, the medical QA, finance domain, coding copilot, and so on. But how does a pre-trained LLM adapt to a particular task? So the thing we need to do here is fine-tuning the LLM on the data from a specific domain. Yeah, so with the advanced development of the LLMs, we have much choice of the pre-trained LLMs, like the Llama or Gamma from Google or GPT, and they have amazing model performance. But on the other hand, they contains like millions of parameters. So in this case, if we want to fine-tune them to a specific domain with all parameters, it will indeed burn tons of GPUs. And of course, it's not eco-friendly. Yeah, and also not much people can afford it. So is there any solution for this issue? A natural thought is that can we do like the fine-tuning more efficiently instead of fine-tuning the whole model? And the answer is yes. So I'm going to introduce one of the most popular parameter efficient fine-tuning method is LoRa. So it's low rank adaptation. It introduced a low rank decomposition to modify the weights from a pre-existing network. So it allows for efficient fine-tuning. So how does it work exactly? So let's see this example. So we have here, you see, input vector x with d dimensions, so which we're gonna pass into the original pre-trained network here with the weights of dimension d times d. And instead of updating all the parameters in the large model, so what LoRa does is it's just a focus on adapting only a small set of auxiliary parameters, which can interact with the original model weights through a low rank metric. So here you see the big A and B. And you see these two metrics, one of the dimension of this metric is R, and R here is way smaller than the dimension D. So during fine-tuning, the original large base model is frozen, and only the metric A and B are trained. From that, this significantly reduce the number of trainable parameters. So it makes the fine-tuning process faster and also less resource intensive. And also, if we want to use it in production, we can just explicitly compute the updated model weights, which equals to the original model weights plus the product of B times A, the matrix. And so we just performing the inference as usual. So this guarantees that we don't introduce any additional latency during the inference. Additionally, swapping only the LoRa weights instead of all the parameters, allowing a cheaper and faster switching between the tasks. Yeah, so that's amazing that we have LoRa technique for the LLM fine-tuning. But actually, we also have another concerns from data perspective. Most of the current LLMs are trained on a vast amount of publicly accessible data. However, despite the fact that more data typically lead to improved performance, some study already show that high quality public data will run out within a few years. And also, if we use the LLM fine-tuning for like personalization of the user data, it will indeed cause the privacy and security concern. And furthermore, there's often a need to build more like specialized LLMs that can integrate the domain specific knowledge so that is not available in the public web-based data. So for example, in the areas of health, law, or finance. Yeah, so federated LLM fine-tuning offer a solution to these concerns, so which allows the individual or organizations to collaboratively improve shared model without sharing their own data. And it provided opportunity, for the privacy protection. Of course, it's careful designed, and also it enables access to a rich pool of the protected data for the LLM training. To do federated LLM fine-tuning, so here we have FlowerTune, which makes the federated LLM fine-tuning very easy. So specifically, it allows the LLM fine-tuning happening locally, and only the LoRa-related parameters will be sent to the server for aggregation. So which typically just less than 100 megabyte. So which makes the message transmission also very efficient. Yeah, so how does the FlowerTune work? So basically, it integrates a bundle of techniques, including first, the Flower datasets, so which you will use to download, partition, and pre-process the training dataset. And then the easy pre-trained LLM adaptation. With that, you can just easily change whatever base model as a starting point to fine-tuning. For example, like a Llama 3 or any other off-the-shelf models. And we also adopt the parameter efficient fine-tuning, the LoRa technique, just as we mentioned before. And also we use the quantization technique during the training for further speed up. And in addition, with the Flower simulation engine, we are able to efficiently make use of the computer resource to do the FL simulation. So all of them come together that makes the LLM federated fine-tuning that can be done just within a single GPU. Yeah, so we have a complete example in the Flower public repo to show how FlowerTune works. So basically, this example is for a general purpose chat assistant. And yeah, let's just see some results of this this example. So if you see the figure on the right, so we benchmarked like 8 open Llama 2 models with FlowerTune on an NLP dataset. And you see that the training loss shows a health drop line in all settings. And also obviously the large base model on the left got a lower the training loss as expected. And as for the VRAM cost, that will be one of the most concern for people, right? So you see the table from the bottom right, only like 22 gigabyte is enough to train the biggest model. And for the smallest model, it only takes around 11 gigabyte. So this means it's easy to fine-tune an LLM in FL setting on a single GPU. So like the 1490 with 24 gigabyte VRAM, and even you can train more than one concurrent clients if you have a more powerful GPU. Yeah, let's see some details of the code. So I just switched to the website of this public example for FlowerTune LLM. And let's just first say the project.toml file. I think my colleague has shown that before. So this file is used to define the dependencies and also the configurations for the experiments. So you see here, it's for the dependencies, so all the required Python packages we need for this example. And so if you moving down to the bottom of this file, you will see a long list of the config for this example. But it's long, but it's still ordered. So you see the different configures is labeled and tagged by with different labels. So for example, here's the configs for model, and the rest is for most of them is for the training. Okay, so let's go back to the code. Yeah, basically it has a similar structure as the Euro Flower example. Maybe let's first take a look at the client app.py. And let's move to the client function. You see, after we load the client partitions, yeah, we will fetch the configs from that TOML file and pass this into the Flower clients. And during the in the Flower clients class, we will see here the feed function. That's the place the training happens. You see, we use the supervised fine tuning trainers to trigger the training, and all parameters will pass into here. And similarly, on the server side, we have the server app.py, and you see it's quite similar to the client side. In the server function, we also like fetch the parameters, the configures from the TOML file, and then we initialize the model weights and define the strategies. Here we use feather average, and then pass into the server app. Yeah, and that's it. Yeah, you see that not just the single example that my colleagues showed in the previous session. Flower can also handle this complex task very easily. So this for the federated LLM training. And apart from that, we also provide a text script here. So this can be used to evaluate your federated pre-trained model and can generate the answer given your querying questions. And yeah, so that's the example. So here, if you see the right part of the slide, we test the FLTrained LLM with a question of what's the ideal day plan in London, and you will get an answer as follows. You see some keywords like the Big Band, House of Parliament, and London Eyes. Yeah, it seems a good plan. And yes, feel free to try the example now. And if you like quite interested in the area of federated LLM fine tuning and want to explore more, and here we have another big announcement. So we will launch a FlowerTune LLM leaderboard. And in this competition, we will release different tasks in various domains with a baseline performance model. It includes the general NLP task, the finance, medical, and the coding related task, and more will come soon. And if you believe your model can beat the baseline, and we invite you immediately submit your code and the model to get into the leaderboard. So how to participate into the leaderboard? That's quite simple. So let me just quickly walk you through the workflow. So yeah, at the first step, you just need to choose a challenge, and then after that, build your training based on the given template. And each challenge has its own specific evaluation metric, and you test your model with evaluation metric to make sure it gets higher performance. And finally, just submit and secure your spot on the leaderboard. Yeah, all right. So this leaderboard will launch very soon. So please scan this code to join Flower Snack and jump into FlowerTune LLM leaderboard channel. And we will keep you updated with the latest news. Okay, so that's all contents of this part. So thank you very much for your attention.
Thank you, Jan. That was great. I think it's amazing to see that the world of LLMs and the world of FL are merging. We can take a couple of questions, probably 3 minutes of questions. I saw there was one person with their hand raised already. Oops, I just accidentally raised my own hand. And let me see if I can find that person. Maybe they put their hand down. On it, we have the person here. He put his hand down again. Could you put your hand up and just leave it up so I can find you on the screen? Okay, great. If I go to the top, I'm gonna so our first question comes from Vitaka. I'm just going to allow you to talk, and could you keep the hand up, and then I can press the button when you put the hand down, then you go back in the list, and it's ordered by name. And so I actually think I found you. Okay. Hi. Let me see. Talking. Yeah. So you can unmute now, and you can ask your question. This is Vitaka. Okay, I think we'll move on to the next person. Next person is our Van Roy. I'll allow you to talk. You can ask your question.
Am I audible?
Yes, you're audible.
Yeah, thanks. Thanks, Nick, and thanks, Jan. Interesting talk. A quick question on this particular setting. Say, when you're talking about a foundation model and say a setting like this, say, is it required to do a transfer learning to set up as a pre-training step on all of the nodes to start with? And secondly is, say, when we are talking about, say, multiple scenarios over here, say, for instance, finance, medical, so each specific transfer learning scenario has to be domain specific when we start training it, as in, say, one model weights can't be used on the other.
Okay, I heard two questions there. First question, yeah, Jan, what do you think?
Yeah, for the first question, yes, it's kind of like the transfer learning. So basically, it's the general fine tuning. You know, we use a pre-trained LLM model which initialized on all the clients at the beginning, and we fine tuning the model only on the lower layers using the client's its own data. And we do the federated training in this process.
And the second question, I think he asked.
The second question, oh, sorry, what's that? I forgot that.
I also forgot.
Could you repeat that, please?
I think it was something about domains. It was like switching from finance domain to something else.
All right. So in the current setting, we only focus on one domain, one by one. I mean, so for example, in the ALP setting, all clients will have the same kind of data from the same domain for the NLP task. But if you like mix the domains in the FL training, it will be, of course, more challenging. But is, for example, you need to some new method to solve this problem. Like maybe we can like swapping, as I mentioned, swapping the lower layers, the lower adapter for different tasks during training.
Got you. Yeah, makes sense. Great. Well, we'll make sure we have time a little bit at the end for more questions. So we'll move on to our next speaker. But thank you, Jan. Great stuff.
Thanks.
Our next talk is going to come from Mohammed Nazari. He is an expert in security and privacy, and also as it pertains to federated learning. So over to Mohammed. We're happy to hear what you have to talk to us about.
Thank you, Nick. I'm just going to share my screen. Sorry, I have to quit and reopen to be able to share the screen. Sorry, just a moment.
Sure, no problem. While Mohammed is reconfiguring his system, we can take a couple of questions. So I've got the channel open in Slack, and yeah, so feel free to ask any questions you might have about this.
Sorry.
Mohammed's back already, so I guess we don't need to answer any questions. Yeah, over to you.
Anyway, can you see the screen now?
Yes.
All right.
Yep, looks good.
Okay, hello everyone. My name is Mohammad Nasseri. I'm a research scientist at Flower Labs. And today we are going to talk about privacy and security in federated learning and generally learn about this area of privacy and security in federated learning. So if you remember from the previous sessions, federated learning basically includes a bunch of clients that they have some local data. And the goal is that we want to train a model using their, oh, there's a question. Oh, sorry. We want to train a model using the local data of those clients, but in a way that we don't want to collect those data. And we don't want to allow direct access to that data. So that's why we have a central server which starts with a model, it sends it to the clients, they train locally, and the server collects the model updates and performs the aggregation part. So just to go over the process again, so we have a global model initialization. So the server initializes a global model with some random parameters, and then it selects some clients. It broadcasts the model to all those clients. Those clients that perform the local training, and they only transfer their updates to the server. The server performs the aggregation, and those steps are repeated until we have a model that is converged and gives us a good accuracy. But we want to focus on this part that the server collects the updates from the participants. And this is the important part in federated learning, that the server doesn't collect the local data. And usually this idea is called minimization. So we should emphasize that federated learning is a data minimization approach. And the data minimization approach is a principle that emphasizes on collecting and processing and storing only the minimum amount of data that is necessary to achieve the purpose. And in this case, the model updates are enough for us to perform the aggregation parts at the server side. And that's why so the data that is locally at the client side is not transferred to the server. But the question here is that since we are not exchanging any data between the server and the clients, can we say federated learning is private and secure or robust as well? And we are going over a bunch of concepts to answer this question. So as we said, the clients, they only transfer model updates with the server. So they send model updates and they receive model updates from the server. So one might say, okay, there are no actual data that are being transferred between these two entities. And we can say federated learning is private and secure. But the problem is that those model updates, they include some information from the local data. Because at the end of the day, those model updates are the output of some training process on the local data. So they include some information and they can leak information. And that goes into the category of privacy. And for the security and robustness, we can say those updates, they affect the model update, aggregated model at the server side. So the clients, they can affect the model at the server side as well. And that goes into the category of robustness and security. So we can have two categories of risk. One is the security, or they call it robustness, which they target the robustness of the federated learning system. And the other is the privacy risk. And the risk is that the adversary can extract sensitive information about the participants' data. As I said, those robustness or security attacks, they target the robustness of the federated learning system. And I just want to emphasize the robustness of the model at the server side. And that model eventually will be handed over to the clients as well. So it affects those clients as well. Usually these attacks are also known as poisoning attacks. And there are two groups of poisoning attacks in federated learning. One is untargeted poisoning attacks. And in this category, the adversary only tries to reduce the utility of the aggregated model. So it wants to reduce the accuracy that you can get in a federated learning system. And the other group is the targeted poisoning attacks. And in targeted poisoning attacks, the adversary tries to make the learned model outputs the target label specified by the adversary on some particular testing examples. For example, if you have an email and you have a model that detects if the email is a spam or not, but the adversary tries to basically make this model to label the email as not a spam when it includes some keywords, for example. Or in this case, we have 3 clients, and the adversary tries to make the global model to label all like bird images as an airplane. And it performs that by sending some poisoned model parameters to the server. And that's why I mentioned that those model updates, they can affect the global model. And eventually this model, which wrongly detects birds as airplane, will be handed over to other clients, and those will be affected as well. And for the group of privacy attacks, the idea is that those attacks, they try to extract sensitive information from the model updates or parameters. So here we have these clients, they're sending their model updates to the server, and the attacker tries to infer some information, some sensitive information about the client's local data from these model updates. Or in a case that we have a deployed model, the adversary tries to infer those information from the global deployed model as well. There are different privacy attacks, but just for the sake of time, I'll explain a bit about membership inference attack. So in membership inference attack, the adversary tries to determine whether a specific data point was part of the training data set or not. To see an example, here we have 3 hospitals. One hospital is specialized in cancer, so it's a cancer center hospital. And suppose this hospital is compromised, so the attacker gets some access to this hospital, and it tries to detect if a specific patient was in the training, in the FL training process for these hospitals. And if it can infer if it was in the training data set, then it can say this patient has cancer or not. And that's a privacy leak, and it's a very sensitive information about that patient. There are also other privacy attacks like attribute inference attack, model immersion attack, or even reconstruction attacks that the adversary tries to reconstruct the whole training data from model updates in federated learning. And usually we have different topics for the threat models. We have insider, outsider attacker. We can have semi-honest or malicious attacker. And the attack can happen during the training phase or at the testing or inference phase. The insider attacker in federated learning can be one of the clients that performs the attack against the server and or the other clients, or it can be the server itself, which tries to perform the attack against the clients. And we should also notice that we can have some federated learning settings that the clients, they don't trust the server. Although they're exchanging model updates, but we should come up with some solutions that allow them not to trust the server, but they share their updates with some privacy techniques, which we will see. And the attacker can also be an outsider. For example, it can eavesdrop on the model updates that are exchanged between the client and server to infer some information. Or, as we mentioned, it can only access the deployed model and infer information about the client's data. The attacker can be semi-honest. So it's passive. It doesn't send any malicious updates, but it only observes the updates. Or it can be malicious. So it can basically change the updates that it sends to the server, or vice versa. It sends from the server to the updates. And it basically goes in the opposite direction of the protocol that we have in federated learning. And the attack can happen at the training phase. During all those steps in federated learning, the attacker performs the attack to infer some information, or it affects the server in the group of robustness and security attack. Or the attack can happen at the inference or test phase. So the attacker doesn't change the target model, but it only queries and tweaks the targeted model to leak some information or produces some wrong predictions. And now that we have talked about all these different kind of attacks and topics in federated learning, let's see what we can do to prevent those kind of attacks, and what federated learning can utilize this because, as we said, federated learning in its vanilla form doesn't provide privacy and security, but we can incorporate those some techniques to provide security and privacy in federated learning. So there are different kind of defenses, differential privacy, secure aggregation approaches, homomorphic encryption, and etc. But today we will cover differential privacy and secure aggregation and how you can utilize those techniques in federated learning and in Flower framework. So let's see what differential privacy is. Differential privacy is a technique that allows performing analysis on some data set in a privacy preserved way. The formal definition is that a randomized mechanism M provides epsilon delta differential privacy if for any two neighboring data sets, D1 and D2, that they differ only in a single record, and for all possible outputs, this equation holds. This might be a little bit complicated, but let's see in simple words what it is doing here. So if you have a data set and you perform some analysis on this data set, I don't know, for example, you do averaging, you're summing up all the numbers in that data set, and then you get one output. And then you remove or add one data point, for example, here, Alice's data from that data set, and in result, you get another data set. It's a new data set which has or has not that specific data point. And you perform the same analysis on that data set, and obviously you get another output. And the idea is that if we give these two outputs to the adversary, and we also inform the adversary that one data record was added or removed from the data set, the adversary shouldn't be able to infer anything about that specific data point. What I mean here is that the inference level of the adversary is going to be bounded. And that is defined by this equation here. And let's say we bound that by some number. We call it privacy budget, and that's epsilon here. And so the lower that number is, the privacy budget, the more privacy you get. And in result, that bounds restricts the adversary to infer information about that specific data record. I see that there is a question, just to see. Are there any plans to natively support homomorphic MPA? If yes, I'll answer this one at the end of the presentation, if that's okay. So that's the idea of differential privacy. Let's see one concrete example to understand it even better. Suppose we have a data set. We have Alice, Bob, and Charlie, and they have different ages. And we also know that they went under different treatments. So two of them, they went under treatment A, one under treatment B, and they got improved or not. So we have these information in the data set. And the hospital, which has access to this data set, wants to publish the average age of patients who received treatment A. So what they do is that they average these two numbers, 25 and 30, and then they output this as the average age. They report this, and they publish this data, and the adversary, who knows that Alice received treatment A, so it has this information, and it also gets this average number, sees the average, and then with these two new, with this data and the data that it already had, it can infer if Bob, it can infer Bob's age, and it can infer which treatment Bob actually had. So this is the privacy leak that might happen if you just output the average of the ages of 2 patients in this data set. But with differential privacy, what you do is that instead of just publishing this number, the average, you add some random noise to that number. And by adding that number, the adversary sees that Alice is 25, but because the average is now different, so it's 28, they cannot for sure tell anything about Bob's age or whether he was treated under that treatment. The important thing is that that amount of noise is calibrated. So you cannot just add some random noise to your data and expect to achieve privacy and also give some information about the data, because this data at the end of the day should have some utility, have some information, and the more noise that you add, you're going to reduce that information. So that amount of noise is calibrated and it's computed in differential privacy. And so the same concepts goes also in machine learning. So if you have a data set, D, and you have a model, you train your model on that data, you get M1, and you add or remove one data point from data set, you get a new data set, you train the same model on that, and you get another model, M2, and these two models, they should be indistinguishable to the adversary, and they should be bounded by the privacy budget, or we can assume some privacy level. There are two main concepts in differential privacy. One is clipping and one is noising. And this is in the, oh, there's a question. A quick question on the attack on training. Data is labeled. How could adversarial attack happen in this step? Let's answer this one at the end as well. So in the clipping part, what it does is that it bounds the sensitivity of the vector that you have, and the noising part, it performs some amount of noise to the vector that you have. And the idea in clipping is that the amount of noise is computed with respect to the sensitivity and also the clipping value that you have. Because obviously, if you're training your model on a data using differential privacy, you cannot just add noise to the model parameters. You need some form of clipping to bound that vector, and then you add the noise. Otherwise, you're just going to ruin the model. There are two forms of clipping. One is fixed clipping and the other is adaptive clipping. So in fixed clipping, you clip by some fixed amount, and in adaptive clipping, you compute the new value every time that you want to perform the clipping part. So let's see how differential privacy can be in federated learning. We will just talk about two variants. So we can have central differential privacy. where basically the server is going to be trusted and responsible for performing the DP mechanism. It means that the clients, they trust the server, so they're sending their model updates to the server, and the server performs the DP mechanism, and it deploys the global model. But that global model is going to guarantee the privacy of the clients. And that is against the outsider adversary that we explained. And in local differential privacy, this is for the case that clients, they don't trust the server. The server can be honest but curious. And that's why those clients, they perform differential privacy locally at their site. And just to explain how it works here. So the idea is that so in central differential privacy, once the server receives the model updates from the clients, it performs some clipping on the updates. Then it aggregates those updates and then adds some amount of noise to that aggregated model and then deploys it. But in local differential privacy, every client is responsible for doing that. So they perform the clipping and noising part locally at their site. So that's why the noising part in central differential privacy always happening at the server side. You can either clip the updates at the server side, or you can do it at the client side. And this is for efficiency. So in Flower, we have two DP strategy wrappers that you can use for your strategy to perform central differential privacy. And the reason that we have two is that one is for fixed clipping, and the other is for adaptive clipping. As I said, fixed clipping always uses one fixed clipping value on every round, but in adaptive clipping, that value is going to compute it on every round. And we also allow to perform the clipping at the client side as well. This is for efficiency, because if you don't do that and all the model updates they send their all the clients, they send their model updates to the server every round needs to go over all those model updates to perform the clipping, and then it performs the aggregation and then adds the noise. But with the help of mods and some clipping mods that we have in Flower, you can basically perform the clipping at the client side and send those clipped updates to the server. The server performs the aggregation and then it adds the noise. And for local differential privacy in Flower, what you need to do is that you utilize the local DP mod at the client side for performing the clipping and noising functionalities. Just to see how easy it is to use differential privacy in Flower. So if you remember from previous sessions that usually at the server side, you have a strategy, and you're using one of the well-known strategy aggregation algorithms, for example, FedAVG in this case, and you want to incorporate differential privacy with your strategy. What you need to do is that you import one of those wrappers that I explained in your code, and you pass the strategy that you have to that wrapper, and then you also need to define some privacy parameters for central differential privacy. So one is the noise multiplier, which defines the amount of noise that you want to add. And one is the clipping norm, and the other is for number of sample clients that are selected on every round, because the amount of noise is going to be computed with respect to that value as well. And once you pass these parameters to your wrapper, then you have a new strategy that you can use, and it is incorporated with differential privacy. And that's for when you want to perform the clipping at the server side. So it's a server-side fixed clipping. But if you want to perform the clipping at the client side, you need to follow the same procedure at the server side. So you have to import the wrapper, but the client side fixed clipping wrapper. And you pass your strategy, your noise multiplier, clipping norm, and the number of sample clients. But at the client side, you need also to pass the fixed clipping mod to the mod's attributes in your client app class. And what it does is that it performs the clipping at the client side, and then once those updates are sent to the server performs the aggregation, adds the noise with respect to these values. So that's how you use differential privacy in Flower. Let's see, there are some questions here. All right, so I'll start with that concludes the talk. That's about privacy and security in federated learning, and how you can achieve privacy with differential privacy in Flower. And let's go over the examples. Sorry, go over the questions.
Okay, the questions. We could start with Daniela. Let me just allow him or her to speak. Could ask your question. Okay, over to you. Feel free to say your question. Daniela, last name Martinez.
There are some questions in the chat box as well. I can answer them maybe.
Yeah, how about starting with them while Daniela.
Yeah. Oh, okay. Daniela, do you want to?
Hi, can you hear me now?
Yeah, we
Yes.
can hear you now. Yes.
Sorry, can you hear me now?
Yes.
Yes, we can hear you.
Yes. So first, thank you for your talk. Really interesting. Just one question regarding the part of DP. Is there a way right now in Flower to calculate the privacy budget spent in the iterations when applying central DP or local DP?
So currently, the way that you can achieve to basically calculate the privacy budget is that you need a moment accountant. And currently Flower doesn't have a moment accountant, but you can import the one that is developed by Google. And you import that moment accountant, you pass the privacy parameters that I explained about, and that accountant is going to compute the privacy budget. But Flower itself currently doesn't have an accountant to track the privacy budget and compute that.
Thank you, Mohammed.
You're welcome.
Great. Yes, let's take the questions in the Q&A box.
Yeah. So the first question is for Jan, right? Okay, second one. Are there any plans to natively support homomorphic encryption? If yes, well. Yes. So homomorphic encryption is one of the techniques that we want to incorporate in Flower as well. The issue with homomorphic encryption is that it's very computationally expensive, and usually it is applied when you have very small number of clients, but it provides a very robust and private setting in federated learning. I cannot say when we can expect it, but it's on our roadmap to provide homomorphic encryption in Flower as well. Quick question. So this is the question from Anirban Roy. So the question is that the edge nodes are already chosen while placing their data for training. How could adversarial attack happen in this setting? I'm not sure if I get the question, but I assume the question is that those clients they don't include malicious or poison data, and how an attack can happen in this setting. I guess this is the question. But so the thing is that poisoning attacks are happening in a setting that you have lots of clients. Those clients, they participate in your FL process. Sometimes you don't know about those clients because you're just participating them in the process because you need more data, you need a better model. And that's why you cannot trust all the clients. In that case, those clients, some of them can be malicious, they can send the poison data. So it's not always that you can assume the clients that you select in your setting are all trusted and they are sending a benign updates. They can send malicious updates. The next question is if you could also...
So yeah, if you could also cover your thoughts on how client unlabeled data could be used. I think it's just asking how would you use unlabeled data in training under FL? Perhaps we could tackle this question at the end if we have time, because
Okay.
I think Jan could answer this quite well, but it's a bit out of the flow.
Okay. I think the next question is also about semi-supervised.
Yeah, exactly. And then the final question we see here is just asking for a link to documentation.
Okay.
Privacy.
All the things that I presented are available on our website in our documentation. But I think that this whole presentation is also recorded and will be shared, right, Nick?
Yeah, that's correct.
Yeah.
Suppose if they go to the documentation, and if they go to the area that deals with DP, they'll see this, I assume.
Yes.
Yeah. Okay. There's a search, I think, in the documentation that somebody could use. If you type in, there's also a search, I believe, in our document.
Yeah. You can search the term differential privacy, and it brings up all the documents available and how you can use differential privacy in Flower, but also what differential privacy in federated learning is. We have some tutorial as well. Yeah, but feel free to use the Slack to ask your questions. We also have a forum, Flower Discuss, for questions.
Okay, well, I think that's we can move on, I believe, to the next speaker. Thank you, Mohammed. Very great information and talk. Thank you. So our next speaker is going to be Pan Heng. He is going to talk about a topic that's closely related because it deals with the same sort of privacy and security issues in different forms. But he's going to be tackling a particular mechanism called secure aggregation, in which he is an expert. So over to Pan. We're really delighted to have you here with us.
Cool. Well, thanks, Nick, for the kind intro. So I'm trying. Let me share my screen first. Cool. Can you guys see my screen?
Yes, it looks clear.
Oh, great. So yeah, this is secure aggregation is also a very heated topic in the area of privacy and security. Especially it has some it also has some pros and cons over the differential privacy one. And as we all know, differential privacy might impact the final performance of the model. So if you don't mind some minor overheads and you would like to have higher accuracy, then secure aggregation is your choice. So just a quick recap. So I believe Mohammed has already talked a lot about what can leak from just from the model updates. So the goal of secure aggregation is actually to find individual model update from the aggregation server, so that the server will only be able to get a aggregated model instead of individual model updates. That can fuse the client updates and makes it harder for the client side to perform attacks on a specific client and then try to dig something out from the model. So here's a not very accurate overview of the secure aggregation. So say if we have 3 clients on the left-hand side, Alice, Bob, and Carol, and each of them hold part of the model update. And they look like part of a digit 1, but it's just for illustration purposes. And in the reality, model parameters won't look like this. But suppose it just looks like this, and each of the client will actually add masks to their local model updates to make it completely random. So mathematically, it is indistinguishable from, this mask model updates mathematically is indistinguishable from a uniformly random sequence. So just from a information theory, you can infer nothing from this mask model update. But with some cryptographic algorithms, it is possible to, like, if the server receives the mask model updates from the client, the server is allowed to and only allowed to unmask the aggregated model. So it can still have a complete digit 1 here, but it does not know which part comes from which client. So how does it work? The first thing I would like to say is that when talk about secure aggregation, in some articles and in some articles they might describe secure aggregation as to securely aggregate model parameters. You can definitely understand it like that, but the secure aggregation we discuss here is a specific technique first proposed by Bonowitz et al. They apply cryptographic algorithms on the model updates, and they do not, and there's no homomorphic encryption included in secure aggregation. And the secure aggregation is more about to securely compute the sum of vectors from the clients. And speaking of vectors, basically means model parameters. And also, when we talk about secure aggregation, I'm referring to a series of protocols like the SecAg protocol, the SecAg Plus protocol, like SecAg protocol for SecAg protocol. So it's not related to homomorphic encryption. And a quick overview is that the key idea in this, the key idea of secure aggregation is pairwise masks. So for each of the clients, it is able to, well, say we have 3 clients here. So for each pair of clients, they are able to generate the identical mask, but one adds those masks and one subtracts the model updates from the mask. So as you can see here, the client 1 add a yellow mask and a green mask. And then the second one also have a yellow mask, but it's right the opposite. So if we sum all these things together, you will find this yellow mask can cancel out each other, and also this green mask can cancel out each other, and also the green mask. And what left is the original model updates. So in that way, although each individual client model update is masked, and it is basically mathematically a random noise. But after we sum them up, we can obtain the accurate global model or accurate aggregate model. So let's go to some crypto insights. So first of all, is noise canceling. So how this is happening? Actually, the idea is very simple. So this established techniques named like Differential key agreement. So it allows two parties to establish a shared secret via an untrusted channel. Well, basically means that I and Muhammad wanted to build a shared secret, and we can only use our phone, which can be eavesdropped. But this is fine. We can use some agreements to generate the shared secret, and no other party except the two of us can know the shared secret. So this is guaranteed by this Diffie-Hellman key agreement. And then with the shared secret, and if we use the shared secret as a seed for a seeded pseudorandom number generator, we'll be able to have a pseudorandom random sequences on both sides, and they are identical. And if for one client, if they add the generated mask to the original model update, and for the other client, it can just subtract the same amount of noise, exactly the same noise from its model update. So if we consider all these pairs masked together for client K, it will compute the noise like this. First of all, it will put the shared secret between client I and itself to a pseudorandom number generator. And if the client I, their index I is less than K, then just add it. But if the client I is bigger than the client K, sorry, the index I is bigger than the index K, then the client K will subtract the noise from the original mode update. This is the noise that will eventually add to the client K's mode update by the client K itself. And if we sum NK together, if we assume all the clients is able to send their mode updates to the server, and if we sum them together, you'll find that these noises cancel out each other and get 0. So although with NK, the mode updates from client K becomes a random noise, but on the server side, it doesn't really need to know the individual client update. You can just sum all the mask models together, and all these noises can be canceled out to each other. And obviously, one problem is that when we talk about cross-device federated learning, it's possible that a device dropped off. It can lost connection during training. So that means if we scroll up a little bit, say if the last client drop out, we won't have green mask and gray mask. That means these two masks won't be canceled out in the final result. So we need to introduce a mechanism for the servers to reconstruct the pairwise masks from the dropped client. So here we use a algorithm called Sharma's secret sharing. So given any secret S, and for secret S, normally it's just bytes. And then we can create n shares, and just n can be anything you like. So we can create n shares. And also, you can use this algorithm and configure it, and then any party is allowed to reconstruct accurately the secret S from any K shares, but will know nothing about the secret S with less than K shares. So this is called K out of N. So as long as I got K clients, then as I got K shares, I'll be able to reconstruct the original secret. So if we apply this mechanism on the secret keys of the clients, then and then if we let all those clients to send a secret share to each of the clients in the training, then even if that client drop out, as long as more than K client survives, the server can ask for the secret share from the surviving K clients, and then reconstruct the secret key of the dropped client. And with that secret key, it is able to the server is able to reconstruct the noises, the pairwise noises of it. So just to summarize, for the most typical, the most classical algorithm, the SecApp protocol, the first step is the clients will exchange public keys. And this public keys is for Diffie-Hellman key agreement, and Diffie-Hellman key agreement is for the pairwise masks. And then step 2, the clients will send secret key shares, and also it's Diffie-Hellman secret key. Send these secret key shares via encrypted channels to each other. And then step 3, clients can send the model with the noise we just talked about. And step 4, the clients will provide the secret key shares for the dropped client, and then the server will recover the secret keys of the dropped client and finally recover the aggregate model by removing the remaining pairwise masks in the aggregate model. So you can already try it out in Flower, and we designed with modularity, flexibility, and extensibility. So it is very easy to use. And speaking of modularity, you can actually we actually implement the secure aggregation as a client mod. So you can basically stack it with other mods like the DP mod. So you can basically stack those mods together. And also it is highly flexible. It is compatible with most of the strategies we provided in Flower. And you're also allowed to extend it, which means you can actually implement your own secure aggregation protocol based on your need. So this is a code snippet showing what we need to do. So if to use Flower secure aggregation, you can just specify the SecApp plus workflow here, and then use SecApp plus mod on the client side, server side and client side. It's small change. And also, super welcome to try out our secure aggregation example in our website. You can go to flower.ai and then go to the example projects, and you will find it. It's named Secure Aggregation with Flower. So, as requested earlier, I'm also happy to talk a little bit about what's the difference between this vertical federated learning and horizontal federated learning. So, the most iconic way of doing federated learning is actually horizontal federated learning, which we assume that we have a bunch of clients, each client have some data, and we can just, and as a server, it can just broadcast the original global model parameters to all the clients, and clients use their own local data to train the local model, and then send the model updates back to the server. And then the server can aggregate those model updates to get a new global model and iterate on. And here we actually assume that data is partitioned on the sample level, or say in the sample space, which means although different clients have different data, but those data, just speaking of each single data point, each sample, or each data sample will have exactly the same features. For example, here, like we have, it's not very clear, but I can read it out. So this is passenger ID, number of children, class, cabin location, sex, title, age, something. So all these clients hold exactly the same features. So they are identical in the feature space. That's why we can directly send the model parameters from the server to the client and let train. But in vertical federated learning, it is partitioned vertically, which means the data are partitioned in the feature space. And that normally means that each single, it normally assumes that each of the client will hold all the data, but they just hold part of the features. For example, here, the client one hold, they also have the ID field, which is the ID column, we'll say, the passenger ID. But for client one, it just has the number of clients, class, and cabin location. And for client two, it holds information like sex, title, and age. And for client three, it has port of embarking, basically the location and fare. Yeah. So each of the clients hold different features, but they hold all the samples. And to facilitate that, one solution is that for each of the clients, it's a little bit similar to split learning, if you guys are familiar with that idea. So for each of the clients, they have their own local model. So here, the local model is not for sharing. They won't be uploaded to the server, actually. It's really local model. They won't be, the parameters or even the model architecture might be kept secret to that specific client. Say, so the client one has a local model, client two has a local model, but different from others. And client three also have a local model and different from the two clients. And for each, and say for each of the clients, say client one will pass its data, its features into its local model and will get embeddings. Or you can understand it's like intermediate output of a neural network. And then with these embeddings, we would directly send the embedding to the server. Similarly, for client two, we also pass this data to its local model and get embeddings and send embeddings to the server. And so for client three, send embeddings to the server. And with all these embeddings, the server will just concatenate all the embeddings together. And then after concatenation, the concatenated embedding will be passed into the global model on the server side, and then get a final result. And then the final result will be put into a loss function. If it is training, then the server will do the backprop until the last layer of the global model. So, and then the gradients will be sent back to each of the clients. So each of the client can continue the backprop until its last layer, and then finally do the update. So it's very similar to split learning. And that's the main difference between horizontal and vertical federated learning. But in reality, there can be a mixture of the two. Say each client, they don't have they don't have all the data, of course, and also they don't have all the features. So in that case, normally you can just create an intersection of all the clients. So, and then we can, and also align those data together so we can do vertical federated learning. Or there's other ways like federated transfer learning to make it, directly train with those highly uneven data, like different samples and also different features. And that's it. Any questions? I think I saw 2 questions. No, they've already answered.
Thank you, Pan. Very very interesting stuff here. I think it's particularly the vertical and horizontal differences and how you can cope with this is an important aspect.
Cool.
Let's see if we have any questions. I don't see anything in the Q&A area. The question is, could multimodal learning be applied for vertical federated learning approach, such as one node performing image and one
First of all, First of all, I would like to say that vertical federated learning is quite different from horizontal one because for algorithms for horizontal category learning, it can generalize to different scenarios. But for vertical one, it is for now at least is highly specialized in specific scenarios. So for sure, it is possible to say one model processing the image and one model processing the audio data, but you might need to design carefully yourself. And each scenarios are quite different in vertical cases. I
Yeah,
hope that
okay, it makes sense. Yeah, that seems good. Well, we do have some extra time, and one thing I wanted to just cover was some slides we didn't show last week.
let me stop sharing.
They are slightly out of order, but I'll just briefly show an overview of the challenges in FL because the main reason we want to we usually present these is that the initial couple of presentations where we introduce the idea, they don't dive into the challenges. We just present how does it work, how is it feasible, what sort of performance you can expect to see. But there are, of course, a variety of challenges, many of which we've been talking about today, how you don't easily get privacy and security unless you sort of work for it, more or less, unless you really think about what you're doing and apply the appropriate techniques. Or when it comes time to tackle different types of models, such as LLMs, you have to think about, well, what's the right approach? And you to introduce new types of facilities like fine tuning. So I think we can, we have 25 minutes. So I can briefly show them. I think that would provide just completeness. So we're being very clear about both the opportunities and we also have included at least an enumeration of the challenges that exist, some of which we've already dived into. So let me just share my screen and show you this. And so with these slides, as I mentioned here, we have a list of the challenges that I'll just go through one by one. They are in no particular order, and they're not meant to be, each one represents quite a rich area of thought, a rich area of examining the problems that can persist within that domain. And also there's always a kind of a complementary set of approaches that can tackle each sort of variation that exists. But if we go through each one that's important to take on board is that, and it's not often highlighted sufficiently, I think, in some of these federated learning papers, is that there's an underlying assumption that the clients are providing not only data, but providing labels, because the learning algorithm that they're adopting within the approach is a supervised one. When it comes time to develop applications and think about practical deployments of these federated learning methods, you often encounter the fact that acquiring labels is not so trivial. You need to build, for example, some sort of GUI, perhaps, that a user might use to label the data correctly. And then, of course, when you have, in this case, users labeling data, they may make errors. They may not be as diligent always. And so then this first challenge is just considering how are you going to acquire your labels if you have an arrangement where you're using a supervised algorithm. As has been asked before, there are less common but increasingly viable methods using self-supervised learning that can overcome challenges of this kind. Jan is very familiar with these. We might tackle them at the end of this. But so the first point here, the challenge is that labeled data is not always sort of naturally available. Second, there is a challenge related to the distributions of the data. And so then if you read works in this space, it's a commonly pointed out concern where you can have this non-IID data arising from the group of clients you're training over. The issue here is that unlike in centralized training, where you have visibility and access to all of the data, it's entirely possible to form, for example, batches from that larger training set where each batch has the same distributions, same underlying patterns, same spread of things like labels and so forth. In the federated case, the issue here is that we have no control over how the data is spread within clients, and within each client, we can only train, especially within those local loops that the clients are performing, they can only train on data available to them. And so depending on how data is balanced and distributed between different clients, different nodes, you can have big variations between the distributions of the batches being trained on one client to the next. There are many reasons for this. They could be based on behavior. So again, if you're thinking of a federated learning example where you are imagining maybe users with an edge device, with a mobile device collecting data, then their own behavior might radically shift the type of data that they collect, which could be quite different to another. This could be related to location. If you're imagining sourcing data from a hospital, then the demographics and the kind of frequency in which certain conditions occur at these regions, at these locations, that can be a reason for this issue. The big issue is that almost all of the learning algorithms that you typically use have an IID assumption about the data they're training over, and federated learning cannot provide us with that nearly as strongly as centralized can. So this is one big, quite enormous area of interest within federated learning. But there are methods that you can use to tackle this problem. Then there's a bulk of factors that all relate to the fact that fundamentally this is a distributed system. What we've done here is that taken two quite complex forms of computer science. Machine learning, obviously, is something that we're sort of barely able to tame, and every day we're learning more about, and we're trying to move from being experimental to more principled. So that's one area. And then we have distributed systems, which similarly is an area that can easily get out of hand in terms of its complexity, how you build algorithms and the software and the whole stack to allow a distributed system to scale, to function, to be maintained. This has been a challenge for computer science for a long time. We've had a lot of success in that area, but it's by no means a trivial thing. And what federated learning is basically doing is bringing these two things together in order to offer some powerful advantages. But through that, you have issues that you see here. Massively distributed systems are possible. When for example, you have a client or nodes in the system that are based on mobile devices, for example, this can be much, much larger than possible. Then you have very unusual learning situations arising from that. So for example, in a federated system, it's quite common for the number of epochs to be very low or even be less than one. And whereas in a centralized case, you might train with epochs of maybe 30, 40, 50, where you've been able to see each data sample more than once, many, many times. In a federated system, because of the availability of devices, because of the size of the data, because of the fact that we want to keep the communication overhead on the wide area network low, you can often see not even all of the data available in the system and have to train on that. As you see here, limited communications, this relates to the fact that within a data center, if you're building a centralized learning system, you can leverage the fact that those links between GPUs and between racks are extremely fast. We even go to the kind of trouble of building bespoke different types of communication protocols and NICs to enable this to happen. And so you can have very fast proprietary links being available in the centralized case that just don't exist within a federated alternative. In the worst case, maybe you're faced with IoT devices or mobile devices where the communication networks are slow, much, much slower, much more brittle. And that even if you have a cross-silo scenario that Javier was talking about last week, even in those cases, those links are still wide area links, and maybe you're experiencing 1 gigabit per second, as opposed to the order of magnitude faster links that you would have inside a data center. Finally, another issue in this dimension of distributed system and the system complexities that Federated brings. You can have varying types of resources between nodes or clients that are participating, which is it was less common in a cloud or data center case. In the cross-device setting, this is kind of extreme. Potentially, you have devices participating together that might have an order of magnitude difference between their memory and their compute capabilities, because even in the mobile phone case, a low-end phone from a few years ago, as opposed and in comparison to a high-end phone of today, they can have that gap. And so how do you combine the contributions of both in those cases and benefit from the data that might be available in the low end case, for example, is complicated. You might not, at the extreme, even be able to have the same neural architecture on all your clients. So that's something that you have to work within and face within federated learning. On the other hand, in a cloud scenario, it's very common for a lot of effort to go into making sure that each GPU and each rack and so on is very homogeneous and basically selected for the task at hand. There's some consideration for, okay, how big is this model? Well, then how big should the VRAM be on the GPUs we're training on, and so forth. But again, there are actually a wide range of techniques that have already been developed to cope with this particular challenge that we're highlighting here. And so it's entirely doable. And when you do it at scale, you can start to access more data and maybe more compute even that you would otherwise have available in a centralized setting. If you're not able to train using this approach with more data than you have available centrally, then something is awry. You should really be using these techniques when they enable you to access more diverse, larger range, larger volumes of data that make all of this worthwhile. And finally, and we've heard a lot about these issues in two of the talks today, there's a wide surface area of challenges that pertain to privacy, security, but also trust and concerns over what is actually happening on the nodes or clients that form your federated network. And so the most important sort of factor you need to keep in consideration is that even though data may not be transmitted for training, it's still possible unless you take the right precautions for training data to be reconstructed at the limit. That's the worst thing, or potentially that's one of the worst things that could happen. And you don't get that facility unless you apply other methods, often multiple methods that complement each other towards stopping this from happening. But again, for almost all cases that people do in the real world, it is possible to protect almost all of the concerns that possibly could come up if you are sufficiently diligent. So that is a quick run through of the challenges, so that we've given a full complement of not only the opportunities, but the kind of other issues you need to concern yourself with, and that also actually drive research, drive innovation out there. So I'll stop sharing. And we've covered everything that we wanted to do in this tutorial. Let's take a look. Anything else question-wise? No. But maybe we could ask, yes, Professor Dubey. I was wondering, what application scenarios do you think are most compelling that you've seen in your area or in your area of interest for federated learning?
Yeah, great. Actually, my the core research area is application of the computer vision in the precision agriculture and in the monitoring of different tasks at the real-time systems. And mostly we apply the computer vision in real time for the monitoring of the electrical gadgets, electrical systems, like the transformer. So there we can think that the application of this federated learning into that area, that how it can work and how we securely we can transmit the signals through some different means. So there are wide scope of this federated learning in the computer vision areas too, and we are looking for those areas that how we can further collaborate and go ahead. I was just willing to ask you that yeah, although you people have set the foundation and you have discussed various models and the challenges of the federated learning. So for the participants point of view, I would like to ask you that in which direction they generally go for the research, and how they can utilize their how can they utilize the federated learning into their research, and you want to set some of the goals for them, so that in the next meeting, in our next meeting, we can even organize another event, maybe after 2 months, 3 months, you can give some open challenges to the participants so that they can start working, they can start implementing the federated learning to solve those challenges, the worldwide challenge which you can give. That would be the best outcome of this workshop, 2 days workshop, if you are willing to share some of the challenges which our participants would like to solve.
Oh, interesting. I think it'd be really interesting to see people try to use federated learning in the scenarios that you were describing. There could be potential for adapting to unusual things in the visual domain that appear, or adapting to a particular some objects and some of these devices that you mentioned, they might appear differently in different locations. And so you could imagine a system that is able to adapt, and maybe with some user feedback, better, basically adapt to the local conditions that they find. I suppose also there might be some just general federated learning challenges that they could take a look at, such as with an existing data set, try to implement or modify an existing algorithm, or and experiment with that. I don't know if Mohammed, Pan, or Jan, you had any interesting kind of examples in that or some other direction that you think would be kind of cool, especially for someone starting out in FL? Like,
Yeah,
what would
actually,
be
sorry. Yeah. Actually, there are different areas, like how can we utilize this in communication? How can we utilize this in image processing areas and the signal processing areas? So we could have clear-cut, problem statement for the particular areas where federated learning can be utilized. And let's see that if any one of you may give some guidelines for the participants so that they can search and they can start thinking, they can start utilizing the federated learning for their good research. And ultimately, we have to think for the society, that how can they try to solve the societal problem through this technique. Yeah.
Yeah, I can talk about the area of privacy and security, and what are the open problems in that area, and what those that are interested in that area can do. One major issue in privacy and security in federated learning is that those techniques they're applied in federated learning setting, but the issue is that how can we interpret those parameters to the users of federated learning. So suppose that if I'm participating in a federated learning process, and the server is telling me we are having some techniques like differential privacy, secure aggregation, but how can we interpret to the user that those techniques are applied and the user is getting the privacy that they desire? For example, Google is utilizing, I guess, differential privacy in Gboard, in their federated learning model for next word prediction, I guess. But how can I, as a user of the Gboard, get to know that differential privacy is applied in this whole process? and what are those levels for the user? This is a really open research area in privacy and federated learning, and I guess this is one direction that that people can investigate.
Yeah, really, that's nice. That's nice that you have given one direction where people can start thinking, and you may even share later on, or Professor Nick, you can share a few of the open challenges which participants may would like to solve it, and that would be for the beneficial of all the society, or maybe it may enhance our collaboration too in future.
Yeah,
Right?
I think
So,
it would also be important to think of things that would be logical first steps for someone who's learning about this for the first time. And then they could kind of build on that towards more sort of aggressive objectives. But for example, managing to take some training data that you have for some applications that you're interested in. You mentioned a couple already. I mean, taking that and being able to federate it would be an interesting step. But we can perhaps discuss offline and come up with some
Right.
suggestions for you. I don't know if Jan or Pan, you had any thoughts. Jan, you were working with an intern recently on a particular topic that might have had other side. I don't know. You might have some thoughts on things you'd like to see people work on.
Right. Yeah. So I think there's a multiple like direction that's quite interesting in the federated learning. So for example, the first thing I want to say is that just as I mentioned in my talk, the large language model is popular and gets amazing performance, but for the fine tuning from a specific downstream task, like a specific domain, is I think it's quite useful for the real applications. For example, like the medical or finance. Yeah, so I think this could be a great direction if people are interested in this. And we also have a leaderboard. We have a wonderful template that people can just build their own data on top of that. That's one thing. And for the second thing, I think is just as Nick mentioned about the challenge of FL, and one of the challenge is the data, the user data is usually unlabeled. And how can we make use of the unlabeled data for training? I think one solution is self-supervised learning plus FL. Yeah, and in this question, like if you considering like a realistic setting, that the user data is enabled, and we make use of the SSL to train the model, use the data, after that we can get useful like the model representations, and that one could be make use also could be used as a starting point for some other downstream task for supervised training, especially for the case like there's not much high quality labeled data. So for example, like the rare language or some rare disease in the medical domain, that could be interesting direction as well. Yeah, so that's how I want to share.
Yeah, that's great. That's great. So, Professor Lane, what do you think? What would be the next to the federated learning thereafter?
Oh,
Yeah.
what's next? I think there's still a lot to be done in the current, but yeah. No, I think that the current form of federated learning is maybe just an initial one. There's probably going to be a proliferation of related approaches that have similar aims. So, so for example, scalably training on private data is increasing in interest, and so one would imagine that that federated learning is a method, but there are lots of variations you could imagine. It's for the different use cases that FL supports. I think that there is enough interest behind those use cases that we'll see a greater set of variations, expand. So FL, for example, FL is commonly this sort of hierarchical topology when it's actually deployed, but there's a lot of interest in decentralized forms of that, where you push the aggregation down in more of a hierarchy. If you're thinking about privacy as a use case, there can be hybrids where you do some computation in the server in a trusted place. Confidential computing is one keyword that people talk about, which I don't think is incompatible with federated learning. It's just a kind of expansion of the approaches. I think it's not a question of like, so for example, I don't think confidential computing is necessarily an alternative to federated learning. It's an expansion of the alternatives to centralized. These are all things that are going to, basically the market share of centralized right now is about 99 to 1. There's like, if not more, 99.9 to 1 for all the training runs in the world. It won't be too long. I would probably say less than 12 months that we'll see that maybe it's 95 to 5, where 5% of the training runs out there are some alternative. It's not purely centralized. We're not copying data into just one place and training on it. But we have lots of variations, bit of processing at the edge, bit of processing with some sort of interesting hardware somewhere in the middle. Could be within a network stack, could be within a data center. It could be with another alternative to this would be multiple data centers working together, which is a sort of unusual form of FL, but I believe it's FL because the core issue is you have a diversity in the training loops, and that the participants within those training loops are not all connected with the same speed and not all logically connected in the same place, and the data is not always available in its purest form directly. So I think that's, so what's next is probably just more of the same, generalization of the core things that are working and becoming more popular is one suggestion. It's a great question, by the way.
Yeah, that's great. That's great. Yeah, because you might be thinking the sustainability of the federated learning, how long it would sustain, and thereafter what would be the next version, or maybe the next thing, which may be the enhancement of the federated learning or something else.
Yeah, but I think like I say, you should think of it more like a proliferation. So it's like, we have maybe one popular way of it right now, and in the future we're going to have 100 popular ways that are variations of themselves. And maybe we call it something different. Maybe they're all just called federated learning. I'm not sure, but yeah. Great.
Yeah.
Well, then I think it's time to perhaps wrap up this tutorial. I can briefly just share this wrap-up slide, if this works. Yes. So this is the end of session 2. This has been a tutorial on federated learning and privacy-preserving methods of ML, largely based on using Flower to perform these common concepts that are increasingly becoming popular, important, and used within the world. It has been a joint effort, joint production with Amity University, Noida, and the CSSP Club. We've loved working with folks such as Professor Dubey here, and many other folks behind the scenes that are not on the call right now, but have enabled the word to get out and help us with publicity and help us with the design of what would be fitting. We'd encourage you all to join the Flower Slack. Many of you already have, or to ask us questions. We're here to help the world perform machine learning in this approach. And we think that students and other members of research staff and so on that we've connected with through this tutorial are the right place to start, so that we can start to change how things are moving forward. Thank you all. It's been wonderful, and we'll stay in touch. We're happy to work with you further.
Yeah, thank you so much. Thank you so much, Professor Lin and Nasiri, Yanga, everyone who have joined these workshops. I'm really very much thankful to everyone, all the participants also. They come forward and they spend time and they learn something from the learned people. And definitely there would be some outcome of this workshop. They have gained some knowledge. They will start thinking over the problem statement which has been given by Professor Lin and Professor Yangao and everyone. So let's hope for the best, and let's see that how it goes on. And further, we will organize some of the good events in collaboration with Professor Lane, and we will devise something that there should be some kind of competition where people can even join and they can utilize the federated learning or even different other AI models for solving some of the challenges. So it's really nice to have the sessions from Professor Lane and his team. So I'm really very much thankful to everyone who have joined the session and who have delivered the.
Oh, you muted yourself at the end.
Sorry. So thank you everyone for joining us. Yeah, it's a great journey, and this 2 days session was really wonderful, and people might have learned many things. Yeah. So it's great. Yeah.
Thank you.